specialized to the case of elliptic curves defined over the rational numbers. And so I gave myself elliptic curve of conductor n. And we saw on yesterday's lecture that this elliptic curve is equipped with a modular parametrization arising from the fact that it's a quotient of J naught of n, one of these quotients associated to modular forms, via the Eichler-Shimura construction. So this is the basic result that Wiles proved, that I explained a bit last week, and that led to his proof of Fermat's theorem. So the goal today is to explain some of the major ingredients that go into the following theorem, which is sort of the main result we have about the Birchman and Dyer conjecture, which says that if the order of so thanks to this modularity, we know that the L series, the Hasebe L series of the elliptic curve, has an analytic continuation in a functional equation and so on. And the result is that if the order of vanishing of this L series is at most 1, at the central critical point, s equals 1, then the rank is the one which is predicted by the Birchman and Dyer conjecture. And also, we'll see as a byproduct of the proof, we also know that the Shafrovich-Tate group of the elliptic curve, which I kind of mentioned a bit last time, which kind of measures the complexity or the lack of effectivity of descent in studying the Mordell-Weil group, this Shafrovich-Tate group is finite, has finite cardinality. Okay, so I'm going to explain now a little bit this proof. And as I already mentioned at the end of my lecture yesterday, the main ingredient are CM points on the modular curve x naught of n, which give rise to a collection of algebraic points on the elliptic curve defined over abelian extensions of quadratic imaginary fields. So I'm going to, in fact, introduce a collection of these points which were maybe studied most intensely, which are the so-called Heegner points. So I'm going to assume from now on, so I'm going to let K be a quadratic imaginary field, which will be fixed in the discussion, mostly. And I'm going to assume so I'm going to make the following sort of Heegner, what's sometimes called the Heegner hypothesis, which is that all the primes dividing the conductor, so all primes L dividing the conductor, are split in this quadratic extension in K over Q. Meaning that, in particular, they're not ramified, so they don't divide the discriminant, and the discriminant of K is a square modulo all these primes, if you want. Okay, so we can always find infinitely many of these by quadratic reciprocity and the Chebotarev theorem, if you want. Okay, so we can find such a K. And now I'm going to consider, so let A be an elliptic curve with whose endomorphism ring. So I really want to look at the endomorphism ring, not the endomorphism algebra. So I'm interested in what the endomorphism ring of A looks like as a ring over Z. So is isomorphic to the ring of integers of K, the maximal order in K. You can write as a Z of 1 plus square root D over 2, where D is the discriminant of this field K, so it's a negative discriminant, of course. So I give myself an elliptic curve with this endomorphism ring, and the theory of complex multiplication tells me that this curve is defined over, not necessarily over K, multiplication, so that A is defined over H, which is the Hilbert class field of K. In other words, the maximal abelian extension of K. Now, the Heegner hypothesis Is there a question? What is it? Yes, that's not what I said? Yeah. So, yeah. No, so H is the maximal unramified abelian extension of K. Yeah. So, okay. So Heegner hypothesis implies that there exists an ideal, which I'll call script n, an ideal of this ring of integers, with the property that the quotient by this ideal is isomorphic to Z mod n Z. So I can take an ideal of norm n with cyclic quotient like that. And, okay, I mean, that's clear, right? Because all the primes dividing n are split in K, so I can choose for each L a prime of norm L and then take the corresponding product, the relevant product. So having chosen this, I can consider the pair consisting of the elliptic curve A and the subgroup of n torsion points of A. So the points on A which are in the kernel of multiplication by every element in this ideal. So this is a subgroup of order n, a cyclic subgroup of order n of A. So this pair corresponds to a point on x naught of n via the moduli description of x naught of n. And moreover, because the endomorphisms are defined over K, so I guess, well, A is defined over H, sorry. So I guess that the endomorphisms are defined over the Hilbert class field, okay? So this subgroup is also defined over H. So this pair gives rise to a point on x naught of n defined over the Hilbert class field. Okay, so I'm going to call this point Q sub n, Q sub 1. Okay, okay, let me just call it Q sub 1. So the point on x naught of n which corresponds to this moduli pair, if you want. And then I'll define P1 to be the image of Q1 under the modular parameterization. So in E of H. And following the notations I introduced last time, I will call P sub K the trace from H down to K of this point P1. I can take the trace because now I'm on the elliptic curve, which has a group law. So this is just the sum over sigma in the Galois group of H over K of the translates of P1 under sigma, and this point is defined over K by its construction right here. So it's invariant under the action of Gal H over K. So it's a K rational point. So last time I explained, or I kind of hinted at the fact, that this result is a consequence of two different theorems. One relating the behavior of these Heegner points to the L series, this theorem of Gross-Zagier, and the second theorem relating these Heegner points and the behavior to the arithmetic of the elliptic curve, its Mordell-Weil group and Selma group and so on. So, and that's the part of the proof which is due to Kolyvagin. So let me kind of remind you of that. And then my strategy in today's lecture and also in tomorrow's lecture is to take the result of Gross-Zagier, this kind of analytic result, as a black box that I won't discuss much, but then try to give you more details on what's in some sense the more arithmetic part of the proof, which is the result of Kolyvagin. So we have this theorem A, which is due to Gross-Zagier, which I mentioned yesterday, that the height, the Néron-Tate canonical height of the point PK. So we saw a little bit yesterday. I mean, I haven't said very much about heights, I guess, in my entire lecture series, in fact. We saw a little bit yesterday in Antoine Chamberloir's lecture that you can define these heights naively à la Tate by taking any kind of naive height on the elliptic curve and then taking the trick of iterating some map, like in the multiplication by 2 map, and then dividing by the degree, and so on, and then getting a number which is somehow more canonical, which doesn't depend on a choice of a naive height function. There is also an approach, in this case, due to Néron, which expresses this height as a sum of local terms, as so-called Néron symbols at the finite places, and sort of Archimedean contributions, which are calculated in terms of potential theory. And that, okay, I mean, so I'll say a few words later about this. So the point is that the Gross-Zagier result tells us that this height, this canonical height, however you define it, is a non-zero multiple of the derivative of the L series of E over K, the Hasse-Weil L series of E over K. So maybe I want to make, I'm not going to say much about the proof, but let me just say that the first remark I want to say is that the proof is really, in some sense, a direct calculation. It's a direct, lengthy, L-E-N-G-T, calculation. Basically, Gross-Zagier compute the left-hand side using the Néron's definition of the height, breaking it up into a sum of local contributions and Archimedean contributions. And then independently, they compute the right-hand side using Rankin's method, which is sort of reviewing this L series as a Rankin L series associated to an elliptic curve and a theta series attached to this imaginary quadratic field. And then having written down somehow these two expressions, they kind of compare and see if they get the same thing. So that's sort of the flavor of the proof. I mean, the proof would take more than, probably, to give all the details would take more than all the time I've been given in this lecture series, so I won't go into it, really. The second remark that I want to make concerns this L series, the L series of E over K. Okay, so we saw that the Hasse-Weil L series of an elliptic curve is expressed as an Euler product, as a product over the primes of K. But because the elliptic curve is defined over the rationals, if you just look at so these are defined for every rational prime, you're going to get an Euler factor which is of degree 4. We saw that the Euler factor is defined in the L series of E over Q is of degree 2, but because now the product is being taken over primes of K, it's sort of that there are essentially two primes. I mean, either one or two, but in the case where there's one, the norm is a square. So you find that when you write out the Euler product defining this L series, you get a sum, like you get a product over rational primes of Euler factors of degree 4 in p to the minus s. Then you can break up these Euler products into a product involving two Euler products of degree 2. And when you work it out, you find that this is the product of the L series of E over Q times the L series of E over Q, the so-called twist by a certain quadratic character chi k. So that you have this kind of decomposition into a product of two Hasse-Weil L series over Q, where, what is this? So chi k is just a quadratic Dirichlet character associated to k. So it's the quadratic character, which I think of as a Dirichlet character. So by class field theory, I can think of chi as a homomorphism from Z mod dz star to plus or minus 1, where d is a discriminant of this quadratic imaginary field. And then this L series is just the sum of an chi sub k of n to the minus s, n going from 1 to infinity. Okay, so this is the sort of twisted L series, and it can be interpreted also as the L series of a certain elliptic curve, which is isomorphic to E over the algebraic closure, but not over Q. It's a so-called twist, which becomes isomorphic to E over this quadratic extension. Okay, this factorization is going to play an important role later. What? Yes, this. Oh yeah, sorry. This is just a quotient. Yes. Gal k over q. You take the unique quadratic character of this, and that's what is identified with the gal k over q. Yes. Sorry. Okay, so this factorization will come up later. So I want to mention it here. Yes. Does not vanish. Does not vanish. Because, okay, so maybe, yeah, so it's good that you mentioned it. So as a corollary, the Heegner point pk is of infinite order. So it's of infinite order if and only if its height is non-zero, and that's true if and only if this derivative of the L series is non-zero. This is a criterion for the non-vanishing of a Heegner point, the non-vanishing of this L series.
But also according to PSD, the radius should be 0.
Ah, good point. Okay, actually, this is okay. Thanks for pointing that out. That's maybe a remark 3 I should make. Okay, the Heegner hypothesis that I made at the beginning of the talk, in which I was used to actually define the Heegner point, okay, implies. So we saw that these L series have functional equations, and so that implies that the sign in the functional equation for the L series of E over K S is -1. So recall that the functional equation relates the value at S to the value at 2 minus S. Okay? So the point S equals 1 is the central point, is the symmetry point for the functional equation. Now, what the functional equation says is if you multiply this expression by suitable gamma factors, then this function is really symmetric about this transformation. It's symmetric when you replace S by 2 minus S, but there is a sign that comes up, plus or minus. So this completed L function is either an even or an odd function of S minus 1. When the sign is -1, this means it's an odd function, so it vanishes to odd order at S equals 1. So that implies that L of E over K S vanishes to odd order. And I mean, this sign can be calculated entirely in terms of local contributions. It's sort of a product of local signs. And the way that I've set it up with this Heegner hypothesis, these local signs, I mean, their product is -1. So it's just a calculation one can work out. So this L function vanishes to odd order. In particular, it vanishes, okay? So that's consistent with the fact that we kind of have a method for producing a point. I mean, sort of a systematic recipe for making a point. Now, this point might not be of infinite order, but at least we know that always the L series vanishes. So that this is somehow the first potentially non-vanishing term in the Taylor expansion of this L series at S equals 1, okay? And it's a general philosophy that, I mean, the derivative would not be a kind of interesting object unless the L series vanished to begin with. And that's the situation in which we are in. Well, that's a good point. There we don't know. So what we know is that the total order of vanishing here is 1. So there's going to be one L series which vanishes to order, I mean, it's odd, sorry. The order of vanishing here is odd, which means that here, one of the L series is going to vanish to even order and the other to odd order, but we don't know which one a priori. We have to compute independently the sign in the functional equation of the L series over Q.
Yeah, but we know it because we know the modularity, right? We
well,
modularity, right? So we know the functional equation for explicitly. Right?
Yes, we know. So we have a formula for the sign. Okay, so maybe this will be remark 4, I guess. So remark 4, if I look at the sign for the functional equation of the L series of E over Q, well, there is a formula for it. I can be quite explicit for it. It's, what is it? It's minus little wn, where wn is the sign of the Atkin-Lehner at n acting on the modular form f associated to E. So you have some involution on the modular curve, which we already used actually last week, so which sends the pair, so it's some involution corresponding to n, and then f is an eigenvector for this involution, and the sign that you pick up is the negative of the sign of the function. Okay? So it's notable that the sign of E over k does not depend on E at all. It just depends on the conductor. It just depends on n, whereas the sign of E over q depends on the elliptic curve via this recipe. So maybe I should call it WNF to emphasize the fact that this also depends on f. not just on the conductor.
And this is not explicit.
Well, it depends what you mean by explicit, right? I mean, you can certainly calculate this numerically very easily on a computer. But it's sort of, it depends on f. So if you just know that you have an elliptic curve of conductor n, you don't know a priori what the sign is. It could be 1 or -1. You want to turn. Okay. Does someone know where the lights are?
Small. Parallel. Two parallel. Yeah, you're right there.
Ah, there, okay. Okay, good. What? F is the modular form attached to E. So it's the pullback of the narrow differential on E via the harmonic parameterization. Okay, so I think those are all the remarks I wanted to make about this result. Now, the second half is this theorem of Kolyvagin. I don't think I need to do that at this stage. No, maybe I don't want to do that. Have I said anything that's wrong? I might at some point, and then stop me if I say something that's false. Okay, so theorem of Kolyvagin, which is what I want to focus on in today's lecture, is that if this point is of infinite order, if pk is of infinite order, then the first thing we can conclude is that the Mordell-Weil group E of k has rank 1. The second thing we can conclude is that the Shafirevich-Tate group of E over k is finite. Okay, so that's what I'll be explaining today, more or less. But I first want to explain to you how these two results imply the big result about version and I over Q that I mentioned before. Okay, so maybe this is, where did I write down this theorem? Yeah, so let me call this theorem maybe GZK or something for Gross-Zagier Kolyvagin. So now let me explain the proof of GZK. So I start with an elliptic curve over Q, okay, whose order of vanishing is not too big. It's at most 1. So then, the fact that the order of vanishing at s equals 1 of the L series of E over Q is at most 1 implies that there exists a K satisfying the Heegner hypothesis and for which, so you see, I start with this elliptic curve over Q whose cell series has the order of vanishing at most 1. If I take a quadratic imaginary field and I look at the L series of E over K, then the order of vanishing is going to be at least the order of vanishing of E over Q. And moreover, I know this order of vanishing is going to be odd because of the Heegner hypothesis. So I can try to find a K for which the order of vanishing is as small as possible. And the smallest odd integer, which is greater than 1, greater or equal to 1, is 1, right? So there exists a K for which the order of vanishing at s equals 1 of the L series of E over Ks is actually equal to 1. So this is a theorem. This is a non-trivial result, but this is an analytic result. This is an analytic theorem on non-vanishing of twists of L series. So you see, if the order of vanishing of L of E over Q is 1, then I need to find a quadratic character chi k for which the twist is non-vanishing. And if the order of vanishing is 0, I need to find such a twist for which the order of vanishing is 1, so the derivative doesn't vanish. And these results were proved by a number of people. They follow, Valence Proof handled the case of the non-vanishing of the value, and then for derivatives, it was done by Bump, Friedberg, Hofstein, and independently by Murty. So there's a number of people who contributed to this kind of non-vanishing results. But that's the first step in the proof. So we give ourselves, in order to study this elliptic curve over Q, we give ourselves an auxiliary imaginary quadratic field for which the Hasse L series vanishes as little as possible. So that's sort of the first step. then the second step is to use the Gross-Zagier formula. So Gross-Zagier tells us then that since this derivative is non-vanishing, that the Heegner point P sub k is of infinite order. And then, applying the result of Kolyvagin, we find that the Mordell-Weil group E of k is generated by this point. So this is a point of infinite order on E of k. And this thing generates E of k up to finite order. So it generates a finite index subgroup of this. And part of the output of Kolyvagin's method is that the Shafrovich-Ch group of E over k is finite. And then, finally, we need a little bit of extra information about this point pk. So extra information about pk. And that extra information is that pk belongs, in fact, to E of q modulo torsion, up to torsion, if Wn is 1. And it belongs to E of k minus up to torsion if Wn equals minus 1. So you see, this point pk is defined over k, but then I can analyze further the action of the Galois group of k over q on this point. And there are explicit formulas for that. In fact, the point is that if you look at pk bar, the complex conjugate of this point pk, then you get what you have to get, namely Wn times pk. So complex conjugation acts like the Atkin-Lehner Wn, and that's what gives rise to that. And that's, of course, exactly what you would expect in light of the formula I gave you for the functional equation of the L series. When L of E over Q vanishes to odd order, then the Heegner point lands in E of Q. When it vanishes to even order, in other words, doesn't vanish, the Heegner point lands in the minus part of this Mordell-Weil group under the action of. And so now you can piece this back together, and you find that the rank of E of Q is either 0 or 1, depending on the sign of Wn, in other words, depending on the order of vanishing of this L series. And then Sha of E over K is essentially a direct sum of the Sha of E over Q and the Sha of E over, Sha of E over Q maps to Sha of E over K by restriction, and the kernel of this map is finite, it's with finite kernel. So the finiteness of this one implies that this is finite as well. And that completes the proof. Okay? Modulo these non-vanishing results and so on. So what I would like to do now is explain a little bit about Kolyvagin's descent argument, which succeeds in bounding the size of the Mordell-Weil group in terms of the behavior of this point pk. So this is a little bit of a negative result in a way. So now I'm going to talk about Kolyvagin's theorem. Okay? I'm going to focus on that. Now, when you first see the Heegner construction, the most striking aspect of it is that it's actually producing a rational solution to the elliptic curve equation from this modularity and so on, right? But then you want a kind of a criterion for this point to be non-vanishing. So Gross-Zagier gives you this criterion in terms of L series. The Kolyvagin's theorem tells you that if the method is successful in producing a point on E of Q or E of K, then this point had to be alone somehow. It has to fill up essentially all of the Mordell-Weil group. So it tells you that the Heegner approach, the approach to constructing rational points on elliptic curves via Heegner points, is never going to succeed for curves of higher rank. So it has this kind of negative aspect to it. But that's life. So anyway, now I would like to explain how Kolyvagin's theorem works, right? So bounding E of K and Sha in terms of the Heegner point pk. And maybe the main point about the argument that one should make is that it exploits the fact that this Heegner point P sub k does not come alone. It sort of comes as part of a large norm coherent system of points defined over various abelian extensions of K. So so the main point is that the Heegner point pk does not, so is part of a norm coherent system of points. So what do I mean by that? Well, instead of taking an elliptic curve with endomorphism by the maximal order of k, I could, so given any integer little n, which for simplicity I'm going to assume is prime to this conductor, capital N, I can consider an elliptic curve having endomorphism, so let maybe A sub n be an elliptic curve with endomorphism ring, end of an, equal to an order of conductor n, which I can write as z adjoint n times 1 plus root d over 2. Okay, so this is the order of conductor n. So it's a smaller endomorphism ring. And you can analyze the field of definition of this elliptic curve. This elliptic curve is n-isogenous to the elliptic curve A with endomorphism by the maximal order. And we know a lot about sort of the Galois action on torsion points of CM curves. We know that the Galois representation cuts out the maximal abelian extension of K and so on. And so the CM theory in this case tells us that AN is defined over an abelian extension which I'll call HN, which is the so-called ring class field of conductor N. So in terms of class field theory, the Galois group of Hn over K is identified with the ideals of K, modulo K star, modulo the product of the, let me give a name to this order, let me call it On or something, the product of the On tensor ZL star, product over all rational L times C star, I guess. Okay, so if this particular, so you know that finite abelian extensions of K are indexed by finite quotients of the ideal class group of K by class field theory. This is the particular quotient which is identified via the reciprocity law of global class field theory with this Galois group. Okay, so it's a certain extension of H1 of the Hilbert class field, which is ramified, as you'd expect, only at the primes L dividing N. Okay. So this all comes out of the theory of complex multiplication. So I can then define, of course, the point QL corresponding, QN corresponding to the pair consisting of this elliptic curve with endomorphism by this order, together with the submodule of script n torsion points on this elliptic curve. And this gives me a point on the modular curve x naught of n defined over this Hilbert class, this ring class field Hn, and then I can take Pn to be the image under phi of this Qn. Yeah.
What is in the denominator there, and what's in the numerator for the Galois?
Oh, everything here is in the denominator. So it's a certain quotient of the ideals of K, by class field theory, and that's what I'm quotienting out by, if I'm not mistaken. Oh, because you're taking the product over all completions, and K is an imaginary quadratic field, so the infinite place is a complex place. Okay, so that's... Or if you want to just take the connected components of the ideals and the... I mean, well, yeah, I mean, you want to modify its connected component. I mean, okay. So that's the thing. And now, what do I mean by norm coherence? So I have all these points, these QNs, right, or these PNs, and I'm going to just state one norm coherence property, which is the only one that Kolyvagin uses in his argument. Someone say? No. So if I have a prime L, not dividing capital N, which is inert in K, so N maybe not dividing capital N or little n, then I can consider the Heegner point P sub NL of level NL, which is defined over the ring class field of conductor NL. And I can try to take its trace from the ring class field of conductor NL down to the ring class field of conductor N. And this is actually related to the Heegner point of level N. It's not quite equal to it, but it's equal after you multiply by this AL, which is the L Fourier coefficient of the modular form attached to E. So you have this identity. So that's the only norm coherence property we're going to use. Okay. And let me give to give you an idea of how that works. Well, the point is that if you take QNL, you take one of these Heegner points. I should say this is true modulo the action of gal Hn over K, I guess. You see, because I was a little bit sloppy in how I chose these ANs. I have many choices, but they're all the same to Galois action. So since I was a little bit vague about that, then they can only have an equality up to translating by the Galois group. But that's not going to be important for the application. So the point is that if you take this point QNL, so this is a point on x naught of n, right? And I can look at the sum over all the Galois translates for Galois HNL over HN. So this is an effective divisor of degree L plus 1. The Galois group of HNL over HN, you can analyze it in, if n is large enough, so in generic situations, this is a group of order L plus 1. Okay? I take the sum of the translate, so QNL sigma. Now, this is equal to what you would obtain by taking the point Qn, which corresponds to an elliptic curve with endomorphism by the order of conductor n, and then taking the formal sum of the L plus 1 points, which are L isogenous to it. So taking the image under the Hecke correspondence T sub L of this divisor of degree 1. With this, I have this equality of effective divisors of degree L plus 1, which are rational over Hn. And this sort of, follows, so again, this is modulo, since I wasn't precise in defining these points, modulo the action of the Galois group of Hn over K. And so, and this follows from the fact that essentially, in the inert case, this elliptic curve A sub n has L plus 1 subgroups of order L, which are permuted simply transitively by the action of this Galois group of the ring. They're all defined over the ring class field of conductor NL, and they're permuted transitively. So you get this kind of equality of effective divisors. When you map that down to the elliptic curve, the TL turns into an AL because F is an eigenvector for TL with eigenvalue AL. So that's the structure of the argument. So that's the main norm compatibility we're going to be using in the argument. So now,
AL is the coefficient of what correlation
to E. So I'm to E, yeah? So AL of E. Because what I'm doing here is I'm mapping these points down to the elliptic curve via this modular parametrization phi. So it can be a bit confusing, right? Because x naught of n is a moduli space of elliptic curves, and it's mapping to this elliptic curve E. Those are two completely different connections between, and E is not CM. E is just your general elliptic curve of conductor n. And right, but then I have this equality of divisors, and I know that phi, if I take TL composed with phi, that's the same thing as taking phi and then multiplying by AL. Okay, so this is really the AL of E that's coming out. Well, not quite, because there isn't a QK in some sense. I mean, there isn't a point on the modular curve which is defined over K. So to go from this P1 or so to K, you just take the trace down to K. But yeah, that's the sort of maybe after the talk. I'm not going to be using the split case at all, but there's a similar formula The difference is that you also have to look at the action of the Frobenius at the primes above L. But yeah, I mean, it's not. I'll do that after. Okay, so let me now prove this result. And I want to kind of explain the Kolyvagin's descent, and what I want to say now in the remainder of today's lecture are sort of the formal aspects of the argument. So the idea is, how do you actually bound the Mordell-Weil group? Well, in yesterday's lecture, I explained a little bit when I discussed the proof of the weak Mordell-Weil theorem, that in order to bound the Summer group, you would try to bound this. To bound the Mordell-Weil group, you would bound the Summer group, right? So. Yes. Well, no, but you see, okay, so I mean so I have a bunch of Pn's. I have a P1, and I have Pk, which is the trace from H down to K of P1. Okay? So P1 is a trace. I mean, Pk is a trace of P1, and P1 is related to the traces of the various Pn's via formulas of this sort. Okay, so that's why. So you sort of think that you have sort of Pk on the bottom, then you have all these other points, and you can kind of get this P1 in many different ways, actually, as traces of points upstairs. And it's this whole collection of points which is going to be used by Kolyvagin in understanding the Summer group over K. You see, because I mean, what's paradoxical about Kolyvagin's theorem when you first see it is that you get the opposite upper bound. I mean, if the Heegner point Pk is of infinite order, that means the rank is at least 1. What Kolyvagin tells you is that if the Heegner point is of infinite order, the rank is at most 1. So this opposite inequality, I mean, uses not just the point Pk, but the fact that there are all these other points, and somehow, well, I'll explain that now, of course. Okay, so so now let me discuss Kolyvagin's proof. So the first point to make about it is that it goes via a P descent. So instead of bounding the Mordell-Weil group, we're going to try to bound E of K mod Pe of K for a suitably chosen descent prime. And we have the luxury of being able to choose our prime P however we want. I mean, we have a lot of leeway in choosing this P. So we're going to fix the descent prime cap a little p in the following way. So I'm gonna first avoid p equals 2. I mean, if you're allowed to choose your prime however you want, the first thing you do is assume it's not equal to 2. And the second thing I want is that the Galois group of Q EP over Q is isomorphic to GL2 of Z mod PZ. So this I can do if E has no CM, if E has no complex multiplication, then it's a theorem of Serre implies, so if E has no CM, a theorem of Serre implies that this is possible, that you can find infinitely many P satisfying this condition. Okay, and it's going to be more, you'll see in the argument. This is just sort of to simplify technically. So I'm throwing out some elliptic curves, I mean the ones with complex multiplication, but it's possible to modify the argument to include those as well. This is just sort of to... But we already had, before Kolyvagin, we already had results about CM elliptic curves following from the work of Coates and Weil. So in some sense, the most exciting case of the theorem, the most novel one at the time, was the non-CM case in any way. So I'll, yeah. Yeah, sorry. I've changed, yeah. In the notations I've been using before, I should really use E square bracket P. Because the module of P division points equipped with the Galois action, and then when the Galois representation has full image, is really the full GL2 Z mod P. And what Serre shows is that, in fact, for all but finitely many P, this is true. So you can do this. Okay, so now I'm going to state the theorem that Kolyvagin proves in terms of this prime P. So Kolyvagin sub P. So it's the analog of the theorem I wrote before, but it begins with the assumption that the image of the Heegner point P sub k in the Mordell-Weil group mod P is non-zero, then the P Selma group of E over K is isomorphic to Z mod PZ. So it's one-dimensional as a vector space over the field of P elements. This is the Selma group I defined yesterday. In particular, E of K has rank 1, and the P torsion in the Shafarevich-Tate group of E over K is trivial. Okay, if I've succeeded in bounding the Selma group, remember, I mean, so why is this the case? Do I stay away from capital N? Actually, no. I don't think I have to in the argument. Okay? So I really only, these are sort of the bad primes as far as the descent prime is concerned. You see, I mean, this theorem, this mod P theorem, does not quite imply the theorem of Kolyvagin that I stated before, because in order to show that the Shafarevich-Tate group is finite, so here I'm sort of controlling the P torsion for almost all P and showing that it's 0 for almost all P. But then I also would need to control the remaining torsion for these sort of bad primes. So it's in my interest to try to keep this set of primes as small as possible. But anyway, I think the most interesting consequence of the result, of the theorem of Kolyvagin is bounding the rank. And that certainly we can succeed in doing by choosing only one of these P's. Okay, so in fact, I will only prove, we will only prove the theorem Kolyvagin sub P for this good kind of descent prime. Okay, so to explain the proof, I'm going to first begin by giving you sort of a general approach to bounding the order of Selma groups. So generalities on Selma groups. And here I'm going to adopt a presentation which, following Wiles, I mean in Wiles' paper, so this of course came after Kolyvagin, but I'll sort of follow that presentation, okay? So I want to present sort of a general machinery which has really nothing to do with elliptic curves in a sense, or with the particular setting in which I am in. So I'm going to place myself first in a slightly more general context to discuss this machinery. And it is useful, actually, in other contexts as well. So Wiles uses this kind of approach to bound the Selma group of the adjoint representation, which is part of his strategy for establishing modularity of elliptic curves. So let me let K here be any number field. And let M be a finite module so really a finite set, which is a module, right? It's a finite module equipped with a continuous action of the absolute Galois group of K. And then I want to study H1 of GK with values in M, which is the group of continuous cocycles on GK with values in M, modulo the group of coboundaries. I also write this as H1 KM, okay? So it's continuous cocycles modulo the coboundaries. Continuous one cocycles, of course, modulo the one coboundaries. Okay, so so I'm going to define a Selmer group associated to K and M in some way, and to a little bit of extra data. Okay. So I want to define Selmer groups. What is a Selmer group? Well, so given a prime V of capital K, I'm going to say that this prime is good if it satisfies the following conditions. So V is said to be good, but this is not standard terminology. This is just a terminology that I'm introducing for the purpose of these definitions. So it's good for M if the following conditions are satisfied. If the first condition is that M is unramified at V, namely the inertia group I sub V acts trivially on M. Okay, so M is a finite module, right? So the action of the Galois group of K bar over K factors through the Galois group of a finite extension. So saying that M is unramified at V is equivalent to saying that finite extension is unramified at V. And another way of saying it is that this inertia group acts trivially on M. Okay, that's the first condition. The second condition I want is that V does not divide the cardinality of this finite module. Okay, so here, in these two conditions, I'm only throwing out a finite set of primes. So obviously, a finite extension has only finite many ramified primes, and the primes dividing the order of M are finite. So almost all primes are good, okay, according to this definition. So if V is good, if V is a good prime, then we have an exact sequence where we can take a cohomology class on KV. So I now look at the local cohomology group of classes on the Galois group of KV bar over KV, this KV being the completion at V. So I can always take such a class and restrict to the inertia group at V. Okay? And of course, a class arising from here by restriction is automatically fixed under the natural action of the Galois group of KV, the absolute Galois group of KV. And the kernel of this restriction map is identified with the cohomology classes which are unramified. KV unram over KV with values in M. Well, you would take the, usually the part fixed by inertia because V is unramified. That's all of M. Yes, I mean, you could certainly do that. You could also say that. I mean, so IV operates trivially there, so it's the same thing, right? I mean, but you could certainly. Okay, so this is just the inflation restriction exact sequence applied to the subgroup IV contained in the absolute Galois group of KV. Okay, so you take inflation restriction, you get that. I'm going to give a name to this map. I'll call it this kind of symbol, circle D sub V. And I'm going to call dV the residue map at V. Okay, so the idea is that, the idea is that when you have a global class, you can consider, of course, the collection of local classes that it gives rise to, and you say that a class is singular if it has ramification, and then this residue map measures sort of the singularity of the class. So you can think of it as kind of analogous to a pole for a holomorphic function or something. And the class will be regular if it's in the kernel of the residue map, and then it kind of comes from this unramified class. Okay, this is just a little bit of terminology. So I'm going to also So I'll call H1 IV M GKV the singular part of the local cohomology H1 KVM. And what else do we want to say? Yes, and then this kernel, this H1, this group that appears here, the H1 KV unramified over KV with values in M. I'll call it the finite part of this H1 KVM. And I'm going to give names to those things. I think I'll call this H1 singular of KVM. And this one I'll call H1 finite KVM. H1 subfinite. Okay, so I guess I want to finish by defining the Selmer group, okay? So, definition. So, a set of Selmer conditions for M and K is a collection of subgroups. So, it's a collection of subgroups, which I'll denote by script LV, contained in H1 KVM, so indexed by all the places V, okay, such that this LV is equal to H1 finite KVM for almost all. For all but finitely many places V. So that's what I mean by a collection of Selmer conditions for H1 KM. Okay? I give myself a subgroup of the local cohomology group at every place V, at every prime V, with the restriction that this subgroup should be the finite classes for all but finitely many V's. Okay, and then if I have such a data, I can define a Selmer group. So let L be a set of Selmer conditions for M and K. Then the Selmer group attached to the triple M, K, and script L is simply what you would expect. So it's the set of all cohomology classes in H1 KM. Yeah, let me cite it again. So it's a set of all classes in here such that the restriction at V of C, in other words, the natural image of C in the local H1 KV belongs to LV. Okay. So here I really want a set of LV. I want an LV for every V. Okay, which is fine because you see I've defined what I mean by H1 finite for all the good V's, which is all but finitely many. For the bad V's, I just give myself some subgroup. It doesn't matter. This condition is that it should be this for almost all V, for finitely many, but I'm ignoring the bad primes in this restriction, right? This makes perfect sense. No. It's you see, you have this exact sequence is on the level of the local cohomology groups, and you have a natural restriction map which goes from H1 Km to H1 KVM by restricting from the global group to the local group. So it's the natural sort of functorial thing that you know. So that's what I mean. So you've given yourself a local subgroup, which is a local condition, and you want that your global class lands in these local conditions at all the for all the V's. Okay, so that's a Selmer group, and I want to just say a few things before ending about these Selmer groups, and we'll continue tomorrow. Tomorrow I'll give a sort of general machinery for bounding the orders of these Selmer groups and show how we can then use the Heegner points to actually make the machine run, so to speak. The main example, yeah. So first, let me mention the main example of a Selmer group is the one where you take M to be the module of P division points of a elliptic curve, okay? And where you let LV be the image of the local points modulo P times the local points under the local connecting homomorphism arising from the Kummer exact sequence, okay? The multiplication by P map and then taking Galois cohomology of that. So we saw this yesterday that this is really, I should say I have a notation for this. I'll call this H1 subscript L Km is the Selmer group, okay? Selmer group attached to the triple K, M, and L. And then in this case here, you see that the H1, for these, in this special case, H1L of Km, obvious to you, then you should work through it. So the general fact is that any Selmer group, if you look at H1 sub L Km, is finite. Okay? So this is for any Selmer group. So you take any finite module and you introduce any set of Selmer conditions, then the resulting Selmer group is always a finite group. Yeah.
Is it necessary to use the condition that LV should contain always H1 finite?
For all but finitely many V?
No, always contain the H1 finite.
No. I want to allow my LVs to kind of move around. So I kind of, for any finite set of places that I care to choose, and you'll see this in the argument, it's useful to have this flexibility of changing the local conditions. So the local condition LV could be 0. You'll see some cases where I'm going to ask that LV be 0, or that LV be all of H1, KV. So I really want to have the flexibility of varying my local conditions. I don't want to insist that it contains H1 finite. But I do want to insist that at almost all V, it is H1 finite. So it's a bit like the definition of Adele's, right? It's a kind of restricted direct product, this LV. It's contained. Yes. Oh, yeah. There's no exact sequence in general, right? Anyway, this module M could be anything. It need not come from P division points of elliptic curves. So, this is just a generalization of this Selmer group, which I defined yesterday. It's a generalization in this precise sense. That if you take M to be the P division points of the elliptic curve and L to be this particular, you have to check this, right? So this is not completely, you have to check that this is indeed, so check that this LV is a set of Selmer conditions. But that I sort of explained yesterday how that goes. So I explained that the image of E of KV mod P is precisely the unramified classes in some way. Okay. And then, so this is a special case of this sort of general construction of Selmer groups. The general fact is that Selmer groups are always finite. And for this, you will need to use the theorem of Hermite-Minkowski, which was also mentioned yesterday in Dan Abramovich's lecture. Okay, so the general problem which I want to discuss in the context of elliptic curves, but it's a problem which comes up in many applications, notably in Fermat's proof, in Weil's proof of Fermat's last theorem and Shimura Taniyama, is to find techniques for bounding the size of this Selmer group, H1 sub L Km. Okay, and so I'll explain that tomorrow, how one goes about doing that. So that's it for my talk today. I want to mention now something about this afternoon's lecture by John Voigt. So here I'm giving you a sort of very general application of the theory of Heegner points, which is to kind of bounding some Mordell-Weil group and getting this evidence for Birchman and Dyer conjecture. But you can also, of course, see the theory of Heegner points as a wonderful method for actually producing solutions to equations in very concrete, specific examples. And in the afternoon lecture, John Voigt is going to show you some examples where you can actually use Heegner points to show that solutions to certain very classical Diophantine problems exist. Okay, so that'll be a kind of different, a Diophantine application of Heegner points with a somewhat different flavor. That's going to be at 2:30, I guess.